Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to calculate the change in free energy for a reaction under non-standard conditions. So in my previous videos we've been assuming standard conditions, which is like 1 atmosphere or 1 molar conditions. But what if you don't have one atmospheres of pressure for your gases, or 1 molar concentrations for your aqueous solutions and things like that? Most things are not under standard conditions. So how would you calculate the standard free energy under non-standard conditions? So in this video, I'm going to go over an example and show you how to do that. So here we go. So in this video, or in this example, we're told to consider the following reaction at 298 Kelvin. So we have 2 NO2 gas plus O2 gas, and that's going to give us 2 NO2 gas. So this equation right here. And so we're given that the delta G standard free energy change of the reaction is a negative 71.2 kilojoules. And then we're asked to calculate the free energy change of the reaction under non-standard conditions. And you'll notice that the delta G here does not have the little circle there. So that little circle you see here, that represents standard conditions. So if you don't see the circle there, that means non-standard conditions. So what are these non-standard conditions? So we're given that the partial pressure of NO gas is 0.100 atmospheres. We're given that the partial pressure of O2 gas is also 0.100 atmospheres. And we're given that the pressure of the partial pressure of NO2 gas is 2 atmospheres. So we're going to figure out what the delta G under those conditions are. So the equation we're going to use is, I'll write it over here, is delta G of the reaction, the non-standard change in free energy, is going to be equal to the standard change in free energy of the reaction. So this is going to be equal to this plus an added part. And that added part is going to be plus, we're adding RT and the natural log of Q, right? So RT and the natural log of Q. So Q, if you remember, is called the reaction quotient. This is with regard to equilibrium things that equilibrium reactions. So here we're going to need to calculate the equilibrium quotient for the reaction. So here we have our reaction, and so Q is set up exactly the same way as K, using the law of mass action. So the law of mass action tells us that Q is going to be equal to the pressures of the products over the pressures of the reactants raised to their coefficient, the powers of their coefficients. So here we have a coefficient of 2, a 1, a 2, and so we'll write those as powers. And so here we go. So we have our product NO, so it's going to be the partial pressure of NO2. Sorry, I think I said NO before. NO2. And since there's a 2 coefficient, we're going to raise that to the power of 2. And then that's going to be over the reactants. And so here we have, again, partial pressure. It will be the partial pressure of NO. Oh, my mistake. I wrote my equation wrong. My equation should be nope, that's right. Just double checking. So yeah, these are actually both products and reactants. Okay, let me double check this. Nope, my bad. This should be NO. Sorry about that. So 2NO gives me 2NO2. So that is the correct one. And so I have that correct there. So that should be NO. And so we got 2NO. So that's going to be the partial pressure of NO. And since I have a 2 coefficient there, that's going to be raised to the 2 power. And then I'm going to multiply that by the next reactant, O2. So it's the partial pressure of O2. And since that's a 1, we'll just raise that to the power of 1. And so this is our reaction quotient expression. So we're going to plug in the values that they gave us. So we have partial pressure of NO2, which is 2 atmospheres. So that's going to be 2.00 atmospheres. We don't need to write in the atmospheres here since our Q value is going to be unitless. So that's going to be squared. And then we have the partial pressure of NO squared. So that's going to be 0.100 squared multiplied by the partial pressure of oxygen, which is again 0.100. So 0.100. So now we calculate that, and when we do that, we get 4.00 times 10 to the third. Let me write that 3 better. So that's third. So that's our Q value. So now we have Q, and we have T, temperature in Kelvin, our R value, right? So what's our R value? The R value is going to be not 0.08206 like we do in the gas laws, but it's going to be with respect to energy, since we're dealing with energy here. So the R value, I'll write it over here. So R is equal to, let me double check. Yeah, 8.314. And here the units are going to be joules, right? Energy over mole Kelvin. So those are the units for our R value. Okay, so we've got our R value, and we know what the standard for energy change, we're giving it there. So then we just plug everything in. So we have delta G of our reaction under non-standard conditions is equal to, and I'll just put in the value, so negative 71.2 kilojoules. Now this R factor is in joules, so we're going to end up with joules. So what we're probably going to want to do is convert this to kilojoule or to joules. So let's go ahead and convert that to joules. And so we'll do that here. I'll show that calculation. So we have negative 71.2 kilojoules over 1. And I know that 1 kilojoule is equal to 1,000 joules. So I have kilojoules on the bottom, so that's going to cancel out here. And then I end up with negative 7.12. Let me make sure I got space here. Yeah. Let me write this clearer. So here I have negative 7.12 times 10 to the 4th joules. So that is the delta G, the standard delta G in joules. So we'll rewrite this in joules. So negative, I have my decimal point in the wrong place here. So 7.12 times 10 to the fourth joules plus R, which is 8.314 joules per mole Kelvin, multiplied by the temperature, which is 298 Kelvin, multiplied by the natural log of Q. And Q we calculated here, so that's 4.003, oops, 00 times 10 to the third. And so now we have everything set up. So now all we need to do is calculate. And when we calculate, we get, let me go ahead and calculate this out for you. So we're going to have that cancel out. And we also have 71. So this is going to be negative 7.12 times 10 to the 4 joules plus, and now we get 2.05 times 10 to the third joules. Okay, and now when we add those together, we get 50, negative 5.07 times 10 to the third, fourth joules, and then we can convert that to kilojoules, so it's going to be negative 50.7 kilojoules for the delta G of the reaction under non-standard conditions. So here you can see that we have negative 50.7 kilojoules under the non-standard conditions that were given here, right? And so you can see if we compare this to this under standard conditions, the standard free energy change, the free energy change of the reaction under standard conditions is more negative compared to under these non-standard conditions. So under these non-standard conditions, the reaction is less spontaneous. Remember, the more negative that your delta G is, the more spontaneous it is. So in this case here, it's less negative, so it is less spontaneous. So I hope, and just a clarification here, you'll notice that I have moles here, but I don't have moles here. It's kind of assumed that this is joules per mole. I'm just not writing down the moles. So hopefully that clarifies that question in case that question came up while I was doing the video and going through the problem. I hope this is helpful. If this explains everything for you, if you found this video helpful in any way, or if you like this video, please like the video, hit that like button. Also, make sure you subscribe to my channel. Hit that notification bell so you can be notified by the videos I put out. Click all so you can be notified by all the videos. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.